Great. So I'd like to introduce Christian Gaetz from MIT, who will be speaking on separable elements, linear extensions, graph associahedra, and splittings of Weyl groups.
Okay, thank you. Thanks for I'm sorry for the mouthful of a title, but I'm trying to cram a few different things into this talk. So all of this is joint work with Ibo Gao. So first I'll tell you about separable permutations and our generalization of these to Weyl groups and some interesting combinatorics related to these. And then in the second part of the talk, I'm going to give some applications of this perspective we resolve a couple different open problems. Okay, so a permutation is called separable if it avoids the patterns 3142 and 2413. So by avoiding a pattern, I mean there's no subsequence of my permutation in the same relative order as either of these sequences. So here I've drawn for you the permutation matrices, if you like, of these two permutations, and you can see they're quite similar. The key feature of these two permutations that separates them from other permutations of length 4 is given in this lemma. So there's an alternative characterization of separable permutations which might be more instructive than just thinking about this pattern avoidance. So I've written it out here, but essentially what this is saying is that separable permutations are those which can be built up from smaller separable permutations by two operations. One is taking direct sum of permutation matrices, that is adding the blocks on the diagonal, or taking a skew sum where you add smaller permutation matrices on the anti-diagonal. So if you look at these permutation matrices here, you can see that these are the smallest ones, smallest permutation matrices that I cannot decompose as a direct sum or skew sum of smaller matrices. So that's why these are not separable, and in fact, being separable is equivalent to avoiding these patterns. So just a little bit of background. So separable permutations have been studied quite a bit. So they were first introduced in the 90s in computer science context. So testing for avoidance of separable patterns can be done efficiently compared to testing for general patterns. They appear in the theory of pop stack sorting. I really like this one, although it's not at all related to the talk, which is that if I have a collection of polynomials and they intersect all at some point, then the permutations that can appear describing how the order of the polynomials changes at that intersection point, those permutations are exactly the separable ones. But what's going to be relevant to us is that there's some interesting combinatorics related to weak order on the symmetric group and more generally on Weyl groups, which is what I'll describe now. So this is the weak order. I'm going to use some notation and terminology about root systems and Weyl groups. Throughout the talk, if you like, you can think of all Weyl groups as being the symmetric group and the simple reflections as being the adjacent transpositions swapping I and I plus 1, and we'll still have results which are new and hopefully interesting in that setting. So the simple reflections are reflections across the simple roots. The length is the smallest number of simple reflections I need to write an element to my group. And such an expression of minimal length is called a reduced expression. The weak order, there's two weak orders, the left and right weak order. So the left weak order has covering relations where I multiply by one of my simple generators on the left. And if that increases my length, then that's a covering relation in the weak order. And similarly, the right weak order is defined by right multiplication. Okay, so a bit more notation here. So lambda of x is the principal lower order ideal generated by x in the weak order, and Vx is the principal upper order ideal generated by x. And in general, whenever I stick a q in front of some subset of my Weyl group, that's just going to mean take the length generating function of that subset. The exception here being that since this upper order ideal has all elements of length at least that of x, we remove that so that this function has a constant term. Okay, so these are length generating functions. Fan Wei in 2012 proved this theorem, which is that if pi is a separable permutation, and I look at the order ideal and order filter in weak order, then these are rank symmetric and rank unimodal, and the product of these length generating functions equals the length generating function of the entire group. So this result was one of the things that first got us interested in this topic. We're going to be generalizing this result to other Weyl groups, and we're also going to prove some results which are new even for this metric group. Okay, so in order to define separable elements in other Weyl groups, I need to define a few more things about Weyl groups and root systems. So the inversion set of a root system, of an element of a Weyl group, are those positive roots which are sent to negative roots. All of these things, I'm going to give an example for the symmetric group if you're less familiar with this setup. It's important that the inversion set uniquely characterizes an element of the Weyl group. And in fact, it's possible to say exactly which subsets of the positive roots can occur as an inversion set of some element. And it's this biconvexity condition here. Furthermore, the left weak order is characterized by containment of inversion sets. U is less than V if and only if the inversion set of U is contained in that of V. Finally, we'll need the root poset. So this is an order on the positive roots where alpha is less than beta if beta minus alpha is a non-negative linear combination of simple roots. Okay, so here's an example for type A, the symmetric group. And if you're less familiar with Weyl groups, then you might want to just think of this case. So here the root system is all the differences of standard basis vectors living inside of this quotient space. We'll call the ambient space that the root system lives in E. The positive roots are those EIs minus EJs where I is less than J. Simple roots are when the indices differ by 1. Reflection across one of these roots has the effect of swapping the ith and jth coordinate living in this space. And so my simple generators, which are those reflections corresponding to the simple roots, are just essentially adjacent transpositions if we identify permutations of these coordinates with the symmetric group. And inversion sets recover sort of the standard notion of what an inversion of a permutation means. And this is a picture of what the root poset looks like. All right, so before I define separable elements, I need one more ingredient, and that's this restriction map first considered in work of Billy and Postnikov. So if E prime is a subspace of the vector space E, then the intersection of that subspace with the root system is itself a root system, and the intersection of the positive roots with that subroot system is a choice of positive roots. So here's the description of a restriction map. Given our element in the Weyl group of the big root system, we know that its inversion set is biconvex. If we intersect it with the subspace, I went quickly over the definition of biconvexity, but it's immediate that this intersection is still biconvex. And therefore, because biconvex sets are exactly the inversion sets, it must be equal to the inversion set of some unique element of the Weyl group of the smaller root system. If that element is W prime, we write W restricted to phi prime is W prime. I think in the interest of time, I'm not going to go through this example carefully, but this is just essentially showing that this restriction map essentially recovers the usual notion of pattern containment for permutations. Okay, so here's finally the definition of what it means to be a separable element in a Weyl group other than the symmetric group. So this is a recursive definition essentially modeled on that second characterization of separable permutations that I gave with direct sums and skew sums. So it's separable if, so first there are two sort of reduction steps. Base case, if any element in the Weyl group of type A1 is separable. If I have a reducible root system, I require all of the pieces to be separable. But the important piece is this third bullet point. And for now, you should just think that this bullet point is trying to model this possibility of having either a direct sum or a skew sum of permutation matrices. So we require there to be a pivot, which is a certain simple root, such that, well, first of all, if I restrict to the subsystem with that simple root removed, then I'm still separable. And also, one of these two things must happen. If I look in the root poset at the roots above my pivot, they must all be inversions or none of them should be inversions. Okay, and this is meant to be the analog of the skew sum or the direct sum of permutation matrices. Okay, so this is best illustrated by an example. So this is the root poset of type B4. And let's suppose we have an element whose inversions are the filled in roots and non-inversions are the unfilled in ones. Then this element is separable. So the reason it's separable is that I have a pivot, which is alpha 3. If I look above alpha 3, all of these elements of the root poset are inversions. They're all the same color, so that's fine. So that's a pivot. And I now reduce to the root system with alpha 3 removed. That looks like this little A2 here and this A1 over here. This is A1, which is a base case, so that's fine. We now have to look at this A2. Again, there's a pivot. Now it's a white pivot. So alpha 1 is a pivot because all of the elements in this subroot system above it are the same color. So that's fine. And then we've finally reduced just to this A1 left over. So that's how we verified that this is a separable element. Okay, in B2, so this is the weak order of type B2. I've labeled the elements by their inversion sets. And the only non-separable elements are these two elements of length 2. So as I was saying, this restriction map models pattern containment. So we say W avoids W prime if there's no way to restrict it and get W prime. And we prove, so remember separable permutations are originally defined in terms of pattern avoidance. We show that several elements of Weyl groups are characterized by pattern avoidance in this sense. Essentially, it's the same two permutations of length 4, these two elements of length 2 in B2, and 6 patterns of length 2, 3, and 4 in G2, which aren't so important because G2 can't really appear as a pattern in anything other than G2. In particular, this shows that the separable elements are exactly the separable permutations because these are the only patterns that could possibly occur in a type A root system. Okay, so this theorem just says that we generalize Fan Wei's theorem directly to this new setup. So if W in any Weyl group now is separable, then the upper order ideal and lower order ideal generated by it in weak order are both rank symmetric and rank unimodal. And the product of their length generating functions is that of the whole group. So this generalization of the definition of separable together with this theorem answers an open problem of Fan Wei about how to generalize her work. One case of particular interest is that the longest element, so this is the element of maximal length in a so-called parabolic quotient, if you know what this means, is always separable. And in this case, we recover this well-known fact that the length generating functions of a parabolic quotient and parabolic subgroup multiply to that of the full group. You might think that, well, in fact, there's a stronger statement than this, which is that if I multiply these group elements by these group elements, I in fact have a length additive bijection with the full group. And that will be demonstrated later for what the proper analog of that statement is. So first, I want to briefly mention a little bit of combinatorics about the enumeration of these and separable elements in connection with phases of graph associahedra. So the graph associahedron is a polytope, which is the Minkowski sum of coordinate simplices corresponding to the connected subgraphs of some graph. The graph we're going to be interested in is the Dinkin diagram of whatever root system we're working in. So in the case of the symmetric group, if that's what you prefer to think about, this graph is just a path graph. So a nested set, these were introduced first, I believe, by Carr and Davidas. And here's some axioms for a nested set. It's a little bit hard to appreciate in a few seconds, but this is some collection of subsets of the graph, which nest inside each other in a certain way. And what's important is that the poset of faces of this graph associahedron is isomorphic to the poset of these nested sets ordered by reverse containment. Okay, how is that connected to separable elements? Well, here it is. So if W is a finite Weyl group and gamma is its Dynkin diagram, then the nested sets on gamma are in bijection with the separable elements via this bijection. So I take a nested set, which is some collection of subsets of my Dynkin diagram. Those subsets, call them J. For each such J, take the longest element of the parabolic subgroup associated to that and multiply these together. Now these don't commute, so I need to tell you the order in which to multiply these, but you should take an order consistent with the nesting. And this will be a separable element, and this is a bijection between separable elements and nested sets. So I should mention that this expression is far from a reduced expression. There's a lot of cancellation that goes on when you do this multiplication. And the rank generating function for the weak order intervals below a separable element then can be given a nice formula in terms of these nested sets. So this rank generating function is just a quotient of two products. N even just means the sets in my nested set which are at an even level of nesting, and N odd are those at an odd level of nesting. And I just take the rank generating functions of those corresponding parabolic subgroups. Now I should mention that each of these parabolic subgroups itself is a product of Q numbers corresponding to the degrees of that group. So this whole expression is really just a product of certain Q numbers over more Q numbers. In particular, the number of separable elements is 2 to the R times the number of faces of all dimensions of the graph associahedron, where R is the number of connected components. This power of 2 is just coming from a technicality where in this proposition, the nested sets are required to contain the whole set. Okay, so now to sort of the second part of the talk where we apply what we know about separable elements to understand what are called generalized quotients. So generalized quotients of Coxeter groups were introduced by Bjorner and Wax in 1988, and they're a generalization of parabolic quotients. So if U is any subset of a Weyl group, the generalized quotient are all of those elements who, when I multiply them with any element of U, the lengths add. And this is called a generalized quotient because they generalize parabolic quotients. What Bjorner and Wax showed, one of the things they showed is that, so this is the join operation in the weak order, so that U is just some subset, but if I take the join of its elements, then the parabolic quotient is actually an interval in left weak order below W naught times the inverse of that element. So any pair of subsets, so these are arbitrary subsets of W, such that the multiplication map, which just multiplies an element of X by an element of Y, is length additive, that is, the length of a product is the sum of the lengths, and a bijection is called a splitting of W. So for example, I referred earlier to the fact that a parabolic quotient times a parabolic subgroup gives me a splitting. Bjorner and Wax, they gave some examples, but they asked, at least in the case of the symmetric group, for which U, in particular, one might focus on the case of an interval in right weak order, is this map a splitting? So this map is length additive by definition, but problem asks which U this map is a bijection. So we answer this question in the symmetric group. So first, in the generality of all Weyl groups, if I'm in a Weyl group and I take the interval below a separable element, so here U is separable, then this is always a splitting of the Weyl group. The converse, and in fact we prove something a little bit stronger than what Bjorner and Wax asked, is that if X and Y are arbitrary subsets of W that give a splitting, so they're arbitrary subsets such that the product gives me a length additive bijection with the full symmetric group, then in fact X equals W mod Y, and Y is the right weak interval below a separable element. So we exactly characterize what are all the splittings. We conjecture that this can be extended to other Weyl groups with the slight additional assumption that U has to be an interval in right weak order, which is, there's something weird which goes on in type F4. So so the last theorem said that this map, the multiplication map here, is bijective if and only if U is separable, where U is the element generating capital U. So we proved this theorem, which is quite simply stated, but was actually probably the most difficult thing we did, which is that for any U, not necessarily separable in the symmetric group, this multiplication map is surjective. Okay, and as an illustration of the utility of this theorem, we'll apply it to resolve a conjecture about linear extensions of posets, or I should say an open problem. Okay, so a linear extension of a poset is an order preserving bijection from the poset to the numbers 1 up to n, and the number of such linear extensions is denoted E of p. The posets we're going to be interested in are two-dimensional posets. So these are partial orders defined by a condition like this, where I've specified a permutation U. So this is one way of defining them. They're determined by the information of a permutation. And the fact that will be relevant to us is a proposition of Bjorn and Wax from a different paper, that these linear extensions, if I think of them as permutations because my elements have indices, then those permutations are exactly the elements of this interval in weak order. Now I need to tell you what the complement of a poset is. So the complement of a poset has its comparability graph is the complement of the original poset. In terms of two-dimensional posets, if the complement of PU can be taken to be PU times W naught. And now the theorem of interest is this one by Sidorenko in 1991, who proved that if P is a two-dimensional poset, then the product of the number of linear extensions of these two, the poset and its complement, is at least n factorial. So this has several known proofs. The original proof of Sidorenko uses max cut min flow sort of argument. It's not very combinatorial. There's a proof of Bolabash, Weyl, and Sidorenko that uses some convex geometry. They use the perfect graph theorem. They use a special case of the Mahler conjecture. So also fairly heavy-duty theorems that don't give us a very explicit understanding of this inequality. So this led Morales, Pak, and Panova to ask for an explicit combinatorial proof of this. These are the number of certain combinatorial objects. This is a nice combinatorial number. There should be some way to see this explicitly. And our surjective theorem gives that. Because, as I was saying, Bjorn and Wax's result relates the number of linear extensions to the size of a weak order interval. That is a parabolic, a generalized quotient times this weak order interval. So for the right choice of U, the size of this U will be the size of this number of linear extensions. The size of this quotient will be this number of linear extensions. And we have a surjection onto the symmetric group. So the product of these numbers must be at least n factorial. We also can refine this inequality by giving a Q analog based on the length of these linear extensions. And that's all I have for you. Thanks for listening.
Great. Thank you so much for the fantastic talk. Let's all thank Christian. And now I'll turn things over to Olya for questions.
Thank you for the talk, Christian. So the first question is from Bruce Sagan. Would you like to unmute yourself?
So yeah, there's been a discussion during your talk about my question, so we thought we should come to the expert. Is there anything known about which intervals in weak order are either top heavy or bottom heavy, where, for example, bottom heavy would say that all the ranks below the middle are at least as big as the rank. This is known for
okay, so what I know about
for a week. Yeah, go ahead.
Yeah, so what I know about that question is, first of all, whenever you have an interval, you can get its dual also as an interval. by looking at the interval below the inverse. So we can just focus on one of them. It's neither top heavy nor bottom heavy in general. It's not rank unimodal in general. But you have to go fairly far before you find those examples.
Gotcha.
You can ask about rank symmetry, and rank symmetry of weak order intervals is not characterized by pattern avoidance. I sort of suspect that separable permutations are the largest nice class of rank symmetric weak order intervals. Maybe one could try to prove something like they're the largest class defined by pattern containment. I'm not sure whether that's true, but there are other rank symmetric intervals, but there doesn't seem to be a nice characterization of them.
But we don't have something similar for like a large, nice class of non-symmetric top heavy or non-symmetric bottom heavy intervals.
Yeah, I don't know anything about that without thinking more.
Gotcha.
The next question is from Grant Barkley. Do you want to unmute yourself?
Yes. So my question was, is the notion of separable still natural if you use the root poset in the non-crystallographic sense? Or more generally, is there an analog of this construction which applies to all Coxeter groups?
Right. So it's possible to work in, so we haven't thought about infinite groups at all. It's possible to work in finite Coxeter groups, but we don't do it for the reason that there's not too much new, not many new interesting cases. So there are the exceptional groups H3 and H4, but those just two cases. And then there are the dihedral groups, but it turns out almost no elements of the dihedral groups are separable. It's just the identity, the simple generators, and then W naught and the things right below W naught. So we didn't bother to work in that generality just because there were no new interesting cases. You could wonder about infinite groups, and there the problem seems to be that this whole notion of pivot and a lot of the theorems we stated rely on the existence of there being a longest element W naught. And so we don't know how to think about this in infinite groups which don't have such a longest element.
Thanks.
Vic, would you like to ask your question?
Really nice talk, Christian. You had that result about the rank generating function for the lower order ideal below this element that corresponds to a nested set.
Yep.
So is there some way to interpret that as the determinant of an algebraic chain complex that's somehow based on the face of the graph associahedra?
I have no idea. That's a very good question. In general, I would like to understand any more. So currently we have this bijection between separable elements and faces of the graph associahedron, but it would be nice to have something which sort of uses the actual convex geometric structure of the associahedron more. And yeah, we don't have anything like that.
Thanks.
And I think we have time for one more question from Federico Ardila.
Christian, thank you for a great talk. I wanted to ask you, so out of all graph associahedra, my favorite ones are the ones coming from Dinkin diagrams because they have this tropical interpretation. That if you take a root system, consider it as a matroid, and take the tropical linear space, then that space is tiled by copies of that graph associahedron. This is something that we showed with Beck Reiner and Lauren Williams. So I don't know if you're familiar with this result or if there might be a connection between that and separability.
I'm vaguely familiar, but not enough to say anything intelligent.
Okay, well then let's all thank Christian again.